Okay, so for module 2, we're looking at scale development and hypothesis testing. So it's important to use good measures because oftentimes in psychological research, we cannot directly measure what we're interested in. So we calculate reliability and validity scores to make sure our measures accurately and precisely describe our construct. We often use scales to label or describe values, and although some people believe that scale use is not justified, Robin Dawes argues that scales could be used in place of a truly representational measure already well established. One of the ways to make sense of our observations and relating them to what we care to know is using the classical test theory. It's also known as a true score model. It tells us that there are two different sources of variability, the true score, which is unavailable to us, and the observed score. Any difference between the two is error. Since variance is really at the core of this test, we take reliability into account because reliability is a ratio of variance. The higher the variance, the lower the reliability, and the inverse is also true. Classical test theory is a collection of many statistical tests, including correlation tests, covariance tests, reliability, sample variance, and standard errors. Now let's take a look at the data set. So here we have a collection of descriptive statistics. Let's first focus on the column labeled skew kurtosis. This describes our distribution. We seem to have moderately skewed data. Our values range from -0.7 to 0.5. We'll be focusing on the variables V1 through V10. We have 10 variables with 30 observations each in our scale. Looking at those measures, our standard deviations tend to fall between 0.7 to 0.9, which are very similar, and our means tend to be negative and fall between 0.07 to 0.4, which vary a little bit more. The last column to the right shows us our standard errors, which appear to be small and relatively equal. To further analyze this data, we're going to take a look at correlation. So I've decided to use a correlation matrix to visualize the data. To get a better understanding of my findings, data inspection is key to identifying data patterns. The correlation matrix indicates a moderate correlation between the data, both negative and positive, ranging from -0.5 to +0.5. The better our correlation, the more reliable our data, so let's move on to reliability. There are multiple tests one can do to get the reliability of a scale or calculate the precision of our measurements. Today, we are using internal consistency reliability, which is known as the average split half reliabilities. Taking all of the possible split half reliability estimates and averaging them gives you Cronbach's alpha. According to Cortina, the coefficient alpha is a stable estimate of split half reliability because there is a substantial randomness component to any estimate of split half reliability. Our Cronbach's alpha will tell us how closely related a set of items are as a group. So for our data, the alpha is around 0.94. It's high, which is great. This indicates strong internal consistency. We've got some negatively correlated items, so V2, V5, and V8, but we've been able to correct for them within the stats package. Now, if we move further along, since alpha is very sensitive to sample size, we want to see what will happen to our data if an item is dropped. The graph on the bottom shows that most of the new alpha scores for a dropped variable are around 0.93. It seems that we have a large enough sample size, even if we do drop an item, because our alphas do not drastically change if we lose an item. So moving on, once you feel confident enough in your scale, you can begin hypothesizing with your data. Hypothesis testing is a statistical analysis in which you place your assumptions about a population parameter to the test to estimate the relationship between two variables. It helps us determine if we are drawing the correct conclusions and are not making type 1 or type 2 errors while doing so. Type 1 errors are committed when the sample results reject the null hypothesis despite it being true. These are inferential errors, errors of permissiveness, and are also correctable. It's also a false positive. Type 2 errors happen when we fail to reject the null hypothesis when it is indeed false. Now, this can occur when we have poor measurements, too much error variance, or when our effect sizes are too small. These are considered errors of conservatism or false negatives. Using our data, I conducted a bivariate test to examine gender, group V11, to our sample, V12. I used a two-sample t-test to determine whether gender had an effect on our population of interest. Our p-value, which represents the probability that the results would occur if the null hypothesis were true, is 0.002. The p-value is smaller than 0.05, which means that we can reject the null hypothesis and state that there are significant differences between our variables. We can proceed to calculating the effect size to better understand the magnitude of the differences found in our data. The Cohen's d is one way to calculate effect size. It's the ratio of signal to noise. This is going to reflect the magnitude of the difference between the two groups in terms of standard deviation units. The greater the value, the greater the effect. In order to calculate this, you take the difference between the two means and divide it by the pooled standard deviation. We're looking for a high effect size between the two groups. We want the means maximally different. In our data, our means are -0.4 and -0.13. Our Cohen's d value turns out to be 0.25, which unfortunately is considered a small effect size. A small effect size would indicate a smaller statistical power. Having the effect size, we can now try to calculate our statistical power. So power is a probability that we will reject the null hypothesis given that the null is false. Power is affected by effect size and sample size. A larger sample size means a larger effect size, and a larger effect size means a larger statistical power. Since our effect size is 0.25, which is considered small, our power will likely be small. These calculations show that our power is 0.15, which is small as projected. Low power means that your test only has a small chance of detecting a true effect, or that the results are likely to be distorted by random and systematic error. Because our p-value is greater than our significance level of 0.05, we fail to reject the null. So our earlier conclusion of rejecting the null correctly is not strong. But Jacob Cohen states that the null hypothesis significance test does not tell us exactly what we want to know. What we're really looking for is, given the null hypothesis, what is the probability that the null hypothesis is true? So he essentially suggests taking the p-value of a smaller than 0.05 rule, just with a grain of salt, and adopt a good enough range null hypothesis and rely more on the rest of the body of statistical techniques we have to work with. That's not all bad. And here we've got our hand calculations.